The dataset consists of a set of measurements from a range of samples. As initially shown, where the etch time is all 0 for all of these data, the data aren't properly organized until we select the Edit Mode button, and the data have been assigned a sample identifier so that each row that were measured from the same sample are all assigned the same sample identifier, and therefore they align appropriately for use in CASA. So for example, TM15, we can look at, say, these three spectra, and if we overlay these, you can see that there's a copper 2p here, and this set represents the Auger and the oxygen peak, and these will be key to the information that we're going to gather from these particular data sets. Another key feature of these data must be that they align well in terms of binding energy, and this particular data set consists of nanoparticles of copper supported on graphite. So if we look at the carbon peak for these three here, and also another carbon peak which corresponds to a pure graphite sample, and we overlay these, and let us just normalize these peaks, and that allows us to see that to a good approximation the graphitic peak from the sample of interest, TM15, and a graphitic peak measured from a graphite sample both align very well in binding energy. Therefore we can assume that we've got a reasonable alignment for these two measurements and any other measurement that we choose to look at. Let's see this one. There's another one that has a good alignment, and another, and let's see this one here, and that's not a good alignment. This shift in binding energy would not work very well for the types of techniques that we're going to apply, so we won't use that sample. What we'll do is we will limit ourselves to only those spectra, and I'm going to select one more, and although there is some kind of movement here, the shape of the peak changing as opposed to the position of the peak. So let's see now if I just overlay those, and you can see that actually this one that appeared to be slightly shifted, well, it's got a lot of structure, and so to a reasonable approximation, I think we can assume that all of these data that I've got selected here will all have a good binding energy calibration. What we'll do now is copy the data that we think has a good energy calibration. That is to say, there's very little shift in energy between these measurements, even though they're from different samples. Because of the graphite, the measurements have nicely reproduced the binding energy for these spectra, and if we overlay them, let's turn off the normalization again so we can see that I've now selected a set of the Auger peaks and also the copper 2p peaks, and I want to combine these together. So first of all, I think I'm going to copy them to a new file, and this will just make my management a little bit easier of what I'm about to do next. So when I select these and I display them one tile per row, you can see that I have now got data organized such that I have the copper 2p and also these Auger. And the reason that I want the Auger is because if we're looking at copper 2p, it's very difficult to tell the difference between the oxidation states, especially for 1 plus and 0, based on the copper 2p alone. However, the Auger peaks are very characteristic of these levels, hence these will be used as part of this analysis. So, having organized a scroll list where each tile contains the overlay of these VAMOS blocks on a row by row basis, if I now bring up the spectrum processing dialog window and I go to the test data tab, we have two options here for merging data. And what I want to do is create, from these two measurements, I want to create single VAMAS blocks that'll be the combination of spectra from two VAMAS blocks, which I will then be able to apply calculated techniques to. So I could either merge irregular, in which case it would maintain the binding energy scale, or in this case I'm going to use merge regular, and that will simply concatenate the auger onto the end of the copper 2p, simply because I selected the copper 2p first for each one of these tiles. So pressing this button means that I've got a copper 2p, I've got the auger, and then I've got a spectrum which is the copper 2p and also the auger, and the auger has been shifted. So now this binding energy here is no longer relevant, but what I'm actually interested in is the shape of these auger peaks and this oxygen peak, and observing how these change as I adjust various parameters in the following analysis so that I can alter the copper 2p. So having done that, what I will do is overlay them so you can see that all these are equivalent, the same. I've got now 4 VAMAS blocks, and each one of these contains a newly created form for the data suitable for the calculator option different spectra, which I'm now going to use to improve my understanding of the copper 2p data envelopes. So the data envelopes that we see here, especially looking at the copper 2p doublet, are really quite complex. If we want to do a peak fit on any one of these, in particular if you try to look at this blue line, the structure that exists in the data suggests that you'd need many synthetic components to try and form an approximation. After providing a background of some description, you'd certainly have a peak model that would be quite difficult to fully understand why you should choose the number of peaks and how you're going to go about fitting them to the data. And that's equally true for this form here, which seems to resemble more of a copper oxide 2+. And here again you've got some combination of this top one, maybe some of the second one, and then in addition it's got this peak which is probably going to be a copper 1+. So the basic idea is to manipulate these data and create some line shapes from these data which we can use to estimate the different proportions of these oxides, different oxidation states within these samples. What is particularly good about these samples is that we've got a set of spectra here that have varying degrees of oxidation states within them. So although this one here probably has a large component of hydroxide, this one here, the structure suggests, and also the peak position of these copper 2p 3/2 peaks, suggests that we've got something that may have a larger proportion of copper 2+. And we've got one here that this structure, well, may well have a hydroxide component with a 1+, and this one here has some kind of oxide. Well, that's consistent with the structure here, but is predominantly a 1+. So we're going to try and exploit the fact that we have these well-defined but merged oxidation states within these data to try and uncover what the underlying oxidation state spectra should look like. So we'll begin by considering 2 of these at a time. Let me just turn off the normalize and the offset. So these are the data that we're going to work with. We're going to bring up the spectrum processing dialog window and go to the calculator property page. The factor, well, we can set that as, let's try 0.5, and we'll use this difference spectra button, and what this button will do is take the 2 spectra in the active tile and the offset here, and it will create a set of synthetic spectra based on the difference between these two in steps of between 0 and 100 in steps of 0.5. So we should get 201 spectra in this new file. So having pressed the difference button, we now have a set of spectra, and we can vary these, and I'm holding down the arrow key, and if you look carefully you can watch this structure here. As I hold the press the arrow key, you can see I'm going down the list. This is the one that's displayed. It's got the red box around it. I'm going down this list, and you can see that as I go down this list of different spectra, this structure here is diminishing. So let's carry on going until the peaks make some physical sense to us. And as I keep going, what appears to be happening is that the proportion of the oxide in the 2+ state is diminishing. Now let's just check what's happening with the Auger peaks. Well, the oxygen peak has just started to go negative here, but the Auger peaks are still looking quite good. We could perhaps justify this dip in the oxygen peak on the basis that oxygen isn't just bonded with copper, there's carbon, and there may possibly be some silicon contamination, something like that, that differs between the two samples. So this structure here may not be as significant as maintaining the shape that we see in the Auger peaks. And we start to get here let's just see what happened, and it went negative. So that is possibly as good as we're going to get. So we'll try that one. Let's take a copy of that. So this is a first approximation to a copper 1+, I believe. So let's save that. And I've just created a new VAMAS block. And that VAMAS block appears here. And that looks like a significant proportion of the 2+ oxidation state has been removed from this, but maybe there is still some structure here. But let's go on down and see what else we can get. The reason it's gone negative is that it's starting to look more and more like the hydroxide state that was also in the data. And let's again look at the Auger peaks, and yes, there's some, although noisier now, we seem to have something that gives us a reasonable approximation to a set of copper Auger, and we've manufactured from the two initial states. Let's demonstrate this. So I'm collecting the first, the last, and this particular one, and I overlay them, and let's just normalize them so we get a means of comparing the initial one, which is the black, the one that was 100, that's the other one that was used, that's the red, and then we can see how the green one we've managed to increase as a proportion of the 1+, the amount of 2+ type oxide, and that means that we've now got two new line shapes, two new forms of the data that we have constructed from the original ones. So let me just copy that. We're now going to return to the data set that contains the newly created vectors, the concatenated vectors, the ones that now give us an alternative perspective of these line shapes. This second pair are copper 2p doublets that have some very distinct characteristics that are different from the first pair. One of them looks like it's got a significant proportion of copper 2 plus oxide, and the other one looks like it's got a significant proportion of the copper hydroxide. So what we're going to do now is go through the same procedure using the calculator property page, and again using the same factor we'll create a set of different spectra, and from these we would like to try and identify doublets that have a greater proportion of the 2 plus oxide and the 2 plus hydroxide. So again, I'm going to slide down this list, and you can see that I've enabled the experimental variable, so it's showing me which one is currently being viewed in terms of the experimental variable. That's obtained by the y-axis, where you can tick or untick these two buttons, and these cause these values to be displayed. So as I carry on down, you can see that changes occur, and you can see that the valley between the satellites and the main primary peak on the 3/2 copper 2p 3/2 peak is changing, and that looks like we've gone far too far. And in order to get an idea of where I am, I think I'll have a look at the Auger and the oxygen, and again we may be overdoing it because we've got a significant negative going oxygen peak. There could be other reasons for that, but nevertheless we'll try and keep a reasonable shape for the oxygen peak as well. And as we do this and you come back, you then end up with a shape here which looks like it could be the major part is the 2 plus. So what we'll do is we'll copy that, and just to go back to the position where we were, I will use the arrow keys and start going again down the list, because what I'm interested in doing now is try to find a different spectra that gives me some of the characteristics of a hydroxide peak, and that looks like it would do nicely. So if I select that one, select this one and overlay them, you can now see that we've got two peaks, two forms, spectral forms that have been derived from the original ones, and they hopefully have the character of the copper hydroxide and copper oxide 2 plus. So let's copy these to a new file. And the other one that we calculated was in the other interpolated one, and I believe it to be this one. So this is the one that has the character of mostly of a copper 1 plus. So we'll take that one through. And the one outstanding question is, have we got any copper 1 plus in any of these two? So let's start off by looking at a difference sequence based on the one that I think looks most like the copper 2 plus and the copper 1 plus. And again we'll slide down that. In fact, what we'll do is focus on the 2p, and what I'm looking at is really this side of the peak. So if I go too far, the peak starts to deform. That's no good. And let's attempt, let's say that looks more like a the shape that I might expect, and there's a lot of trial and error involved in this. And I'm going to copy that now into this new one. So that's my new and improved version of the copper oxide 2+. So now let's do the same with the hydroxide. That's what we want to try and work out, the proportion of this that's still involved in the copper oxide, hydroxide here. Doesn't look like it's much, but nevertheless we'll do the same trick and we'll look at a difference spectrum. I'll just zoom in so we can highlight it. So I think we're probably good there. So let's now copy that one also to the one that we're collecting the data in. So we've got here the copper 1+, and these are our first approximations based on different spectra using the particular samples in question for giving me line shapes from the data that we can now fit back to the original data, namely all the different TM samples that were measured previously and in the original file. So in order to do this, what we have to do is create line shapes from the data, and let's do this by creating a background type. That's aimed at the three sets of data that we think are best suited for representing the different oxidation states. And I've just propagated the backgrounds, and let's display them all, and we'll look at the region and offset them so that we can see. And the background looks good enough, it's not cutting through the data anywhere, so we'll use that as the background type, and it's a U2 2 guard, and I've got the parameter is -1850, and that's why it has got much shape in it and is a concave up shape. So let's prepare these for line shapes now, and to do that we'll use the test data tab, and we will background subtract each one of these. I'll propagate that operation to the other two, and then we'll copy them in the process data only form. So now I've got extra VAMAS blocks. Each one of these is now without a processing history, and this is now the data that's saved in these VAMAS blocks, so they'll be suitable for line shapes. The original ones have a background subtraction operation on them, so I can undo those. There you go. And what we'll do is we will convert these to have key characters and some description of what they are. So this is going to be %, less than, greater than Cu2+. This one is the hydroxide, so we'll call that %, less than, greater than Cu hydrox, and this is going to be our 1+. So the %, less than, greater than gives us an extended form for managing line shapes that are more than just a simple Gaussian Lorentzian. So these are essential for extended energy intervals such as these, for representing a whole set of peaks rather than just a single peak. And we can just get their positions by creating a component, and what we'll do is we will copy that name, is used as the name for the line shape, and when I press enter it says, would you like to fix the full width half maximum to unity? And the answer is yes, because we do not want the full width half maximum to adjust when it does the fitting, otherwise you can end up with peak positions moving relative to one another. So that is an essential feature, to have it locked. And when I say fit, it fits it to the data. You can see that now that's the line shape fitting the data very well. I'm going to do the same for the hydroxide. Create a peak, give it a name, and say fit. And the reason that I'm doing this part is so that when I go to my next file, I have these line shapes available to me. And I can tell whether I've got line shapes available if I hold the control key down before this is an edit field and I click. It will show me a list of the line shapes that I've got. So these were two default ones that were already there, and these two have been added as I've been creating these line shapes here. So now I'm going to go and do the last one. And again I'm going to fit it. So now I've got line shapes fitted to the original data, and this is important because now I can actually take these and copy them. So for example, I can take this one here, which is the hydroxide, and I can copy this and I'll paste it, so we can now see that we've got more than one line shape there. And I'll do the same again for the copper 1 plus, and I'll paste it. So you can now see that I've got all of the line shapes involved in this peak model, and they've all got the same position that has been set up by fitting them to the data. So I can now take the position constraint, and if I say lock and press return, you can see that each one of these has been given an offset from the component in column A. So in other words, in this case, it's the one in column A is the copper 2 plus oxide. The one in column B is the copper hydroxide, and the one in column C is the Cu2O. One plus. So now I've named these components. Perhaps we'll give that a CuO. I've got these components now set up, their offsets are fixed, and we can now use them to model other data. So I'll copy all of these, I'll go back to my original data set, and let's get rid of the spectrum processing. Let's go to 15, and we'll give it a background. It'll remember the background we used last, so we just have to adjust the limits, and then we can replace the components into this, and then say fit, and we get a good fit. We can get an extraordinarily good fit, in fact, and that's because these data were used in constructing these peak models in one form or another. There was more than just this data, but nevertheless the difference between TM15 and the other samples were used, so that's why the residual is rather good. However, we have another example here of TM15, which is a distinct measurement. So it's the same sample, but the spectrum was measured again. So if I propagate these to this second measurement and then look at it, you can now see that we've got a fit, and the fit is consistent with what you'd expect for Poisson statistics, that it's about unity. So you can say that what we have is a peak model that will work for the TM15, and we might want to just check it one further case or two. If we go for, say, let's do TM19 and TM10. So if I propagate these again, I won't fit them this time. Let's just have a look at them before we fit them. Now this one's got quite a different shape, so what I will do is I will copy all and I'll paste replace so that they are now in the right order of magnitude, and so we've now got a model that is working reasonably well. A bit we have some data that's not particularly good here. Let's go and have a look at another one here. Let's do so I've already got a peak model on there, and if I say fit to this one, and this TM19 has again given a very good fit. It's got, let's compare it to 15. I'll turn off the residual and stack them. So although they are reasonably similar, these two, let's just see which is which. So the black one is TM19 and the red one is TM15, and although they're very similar, they both fit quite well. The amount of hydroxide is perhaps slightly different. Let's exclude the line shape and the 4/12 maximum and apply. I'll just propagate that to the other one. So you can see that you get a reasonably similar proportions of the different components that we've constructed, but both produce a reasonable fit, and that leads you to believe that we're on the right track, but we need to do a little bit more work in order to accommodate the TM10, for example. It looks like there's something else involved here that might suggest that we have to do a little bit more work on constructing a line shape that will accommodate these parts here.